Today, section 2.6 again, 3 topics. Topic 1, continuity checklist. Topic 2, the intermediate value theorem. Topic 3, more examples. Take a review about what we learned in the last class first. A curve is a continuous curve if the curve can be drawn without removing your pen from the paper. B, a function is a continuous function if the graph of the function is a continuous curve. C, what functions must have continuous graphs? The answer to this question is functions that are not intentionally constructed. Not intentionally constructed. Precisely. Not constructed piece by piece. Not defined piece by piece. Functions that are not intentionally constructed are continuous everywhere on their domains. Now, topic 1, continuity checklist. Given a function f and a point A on the x-axis, if the following 3 conditions hold simultaneously, then the function f must be continuous at a point A. Condition 1, the function is defined at a point A. Namely, the graph of the function at a point A has a solid dot. If the function is not defined at a point A, then the graph at a point A will have an open dot. Therefore, the graph will have a break at a point A, not continuous. Condition 2, the both-sided limit at point A exists. Namely, the graph has no jump at point A. This case, the both-sided limit at point A exists. No matter how x approaches A, from the left or from the right, the curve approach the same point. When the graph has a jump at point A, then the both-sided limit doesn't exist because the left-hand side limit and the right-hand side limit different. Condition 3, the both-sided limit at point A is equal to the function value at point A. Namely, the open dot and the solid dot at point A coincide. Open dot is the limit. Solid dot is function value at point A. This case, the graph is not continuous at point A. Only when we shift this solid point here, the graph becomes continuous at point A. These 3 conditions are called a continuity checklist. Here is one example about the continuity checklist. Determine whether the following functions are continuous at point 2. Use the continuity checklist to justify your answer. Sketch the graph of the function. Now, the function in part A. This function is not defined at point 2. When we plug in 2 in x, then we have 0 over 0, not computable. So condition 1 in the continuity checklist is violated. Therefore, the function is not continuous at point 2. Here is the graph of this function. At point 2, low function value, so there is an open dot. The graph has a break at 2, so not continuous at 2. While the graph of this function is a line, simplify the function, then we see that this function is equal to x plus 1. The graph of x plus 1 is a line. This function and x plus 1, they are equal everywhere except at point 2. At point 2, this function has low function value, but this function has a function value. The function value is 2 plus 1, 3. The function in part B is defined at point 2. When x is 2, function value is 1. So condition 1 in the continuity checklist is satisfied. Now we want to see whether or not the second condition is satisfied. So we compute the limit at 2. Recall the convention about a limit. X approaches 2 in this process. We don't allow x take the point 2 directly. So we have this equation. When x is not equal to 2, by the definition of the function is this rational function when x is not equal to 2. Plug in this rational function in f here, then we have this equation. To compute this limit, we can use direct substitution. Plug in 2 in x, then we have 0 over 0. We cannot tell the limit. So we need to simplify the function. Factor the polynomial on the top, then we have this equation. Cancel x minus 2, then we have this equation. Now, to find this limit, direct substitution. Plug in 2 in x. So the limit is this number, the number 3. Therefore, as x approaches 2, the function approaches 3. Condition 2 is satisfied. However, condition 3 is not satisfied. The limit at 2 is 3. This limit is 3. But the function value at 2 is 1. They are not equal. Therefore, the function is not continuous at point 2. Here, this is the graph of the function. At point 2, the function has a break. When we draw the graph of the function at point 2, we have to remove our pen from the paper. Then plug this solid point, then go back to draw the line. Now, topic 2, the intermediate value theorem. The first theorem in calculus 1 is the squeeze theorem. Squeeze theorem is in section 2.3. The theorem essentially says that if two curves approach the same point, then any curve between them will also approach the same point. This diagram shows one example. The intermediate value theorem, IVT, in this section is the second theorem in calculus 1. IVT essentially says that a continuous curve cannot jump over a horizontal line. A curve that is not continuous can jump over a horizontal line. But a curve that is continuous cannot jump over a horizontal line. A continuous curve must intersect the horizontal line at least once. Here is the intermediate value theorem. Suppose function f is continuous on the closed interval AB. Say the graph of the function is this curve. And suppose the horizontal line L lies between function value at A and function value at B. Function value at A is this point. Function value at B is this point. The horizontal line L is between this point and this point. Then, conclusion. There are XX at least one point C in the open interval AB. Open interval doesn't include the two endpoints. So C is in this open interval. That means that C is between A and B. Then there are XX at least one point C between A and B such that function value at C is equal to L. In this diagram, there are three such points: this point, this point, and this point, where the function values are equal to L. In IVT, in this theorem, continuous is a keyword. If the function is not continuous on the interval AB, we don't have this theorem. For example, the function in this diagram is not continuous everywhere between A and B. At this point, the function has a jump. For this function, you cannot find a C between A and B. There, the function value is L, because the graph of the function doesn't intersect the horizontal line L. One application of IVT is in locating roots of equations. Here is one example about how to do that. Given this equation, A, use IVT to show that this equation has a solution between 0 and 1. B, use a graphing utility to find all the solutions to the equation in this open interval. The intermediate value theorem has two conditions. Condition 1, the function f should be continuous on the interval AB. Condition 2, the horizontal line L should be lie between the function values at the two endpoints of the interval. If these two conditions are satisfied, then we have this conclusion. Between A and B, there is a point C where the function value is equal to L. To answer part A, in IVT, I set the function f to be the function on the left side of this equation. The interval AB to be the interval from 0 to 1. The horizontal line L to be the number on the right side of this equation. Because this function is not a function intentionally constructed, namely, not a function defined piece by piece. This function is continuous everywhere on its domain. The domain of this function is any number, all the numbers. You can have a try with your calculator. This function is computable at any number. So the graph of this function is continuous from negative infinity to positive infinity. In particular, the graph of this function is continuous from 0 to 1. Therefore, condition 1 in IVT is satisfied. Now, have a check with the second condition. I want to see whether or not L is between the function values at the two endpoints of this interval. Compute function value at the left endpoint. A now is 0. Plug in 0 in x, then we get the function value is 1. Function value at the right endpoint. Plug in 1 in x, then the function value at the right endpoint is 4.7, 183. Now, L is 3, so L is greater than this function value and less than this function value. So L is between the function values at the two endpoints of this interval. Second condition is satisfied. Now, conclusion. So by IVT, there is a point C between 0 and 1. There, the function value is 3. This point C is a solution of this equation. IVT only says that between A and B, there is a point C where the function value is equal to L. This theorem doesn't tell us the exact value of the point C. To find the exact value of the point C, we need to plot the graph of this function and also plot the horizontal line. Here, I plot the graph of this function and the horizontal line. The horizontal line at 3. Then the x-coordinate of the intersection point is the exact value of the point C. In this example, the exact value of the point C is 0.5942. Topic 3. More examples. Example 1. Given this equation and this open interval. Part A. Use IVT to show that the equation has a solution on the given interval. Part B. Use a graphing utility to find all the solutions to the equation on the given interval. To answer part A, in IVT, I set the function f to be this function, and the interval AB to be the interval from 0 to 1, and the number L to be the number on the right side of this equation. Because this function is not a function intentionally constructed, not a function defined piece by piece. The function is continuous everywhere on its domain. This function is quite complicated and it is difficult to determine its domain. But it's easy to see that the domain of this function contains this interval. Because with a calculator, it's easy to see that the function is computable at any number in this interval. So the domain of this function contains this interval. Therefore, the graph of this function is continuous everywhere in this interval, on this interval. So condition 1 of IVT is satisfied. Now, condition 2. Compute function values at the two endpoints of this interval. Function value at 0 is this number. Function value at 1 is 6. L is 5, so L is between function value at left endpoint of the interval and function value at the right endpoint of this interval. So condition 2 of IVT is satisfied. Now, conclusion. Between 0 and 1, there is one point C such that function value at C is 5. And this number C is a solution of this equation. Part B. I use my computer to plot the graph of function f. This curve is the graph of function f. This horizontal line is the horizontal line at 5. From this diagram, between 0 and 1, the graph of the function and the horizontal line have only one intersection point. Only one intersection point. And the x-coordinate of this point is the exact value of point C. The exact value of point C is 0.8343. Example 2. Consider this function. This function is defined piece by piece. Function value at 1 is A. Now, part A. Compute the limit, the left-hand side limit at 1. Then determine the value of A for which the function is continuous from the left side at 1. B. Compute the right-hand side limit at 1, then determine the value of A for which the function is continuous at 1. Solution to part A. Compute the left-hand side limit at 1. X approaches 1 from the left side. X approaches 1 from the left side. So X is less than 1. By definition, when X is less than 1, the function G is this function. So we have this equation. Now, to find this limit, direct substitution. Plug in 1 in X. This limit is this number. This number is 2. This is part of the graph of function G. At 1, function value is A. When X approaches 1 from the left side, function approaches 2. So the graph approaches this point. The height of this point is 2. Now, to make the graph continuous from the left side at 1, we need to shift this solid point here. So we need to set A to be 2. Conclusion, for G to be continuous from the left side at point 1, A must be 2. Part B. Compute the right-hand side limit at 1. Then determine the value of A for which the function is continuous at 1. This continuous is a both-sided continuous. That means that continuous from the left side at the same time continuous from the right side. Right-hand side limit. X approaches 1 from the right side. X approaches 1 from the right side. In this approaching process, X is greater than 1. By definition, when X is greater than 1, the function G is this function. So we have this equation. To find this limit, plug in 1 in X. The limit is this number. This number is 8. Here is a possible sketch of the function G. At 1, function value is A. From part A, X approaches 1 from the left side, function approaches 2. So the graph approaches this point. This point is 2. The height is 2. From part P, when X approaches 1 from the right side, function approaches 8. So the graph approaches this point. This point, the height is 8. When we shift this solid point here, then the graph is continuous from the left. When we shift this point here, then the graph is continuous from the right. Because the graph has a jump, no matter where we place this solid point, we cannot make the graph continuous from the left side at the same time continuous from the right side. So the conclusion is the function G is not continuous at 1 for any value of A. This continuous is both-sided continuous. Example 3. Consider this piecewise defined function. A. Use continuity checklist to show that the function is not continuous at point 0. B. If the function continuous from the left or from the right at point 0. C. State the intervals of continuity. Here is continuity checklist. If these 3 conditions are satisfied, then the function f is continuous at point A. The point A in this example is 0. Now, I want to see whether or not the function f is defined as 0. From the definition of the function, when x is less than or equal to 0, the function is this polynomial. So function value at 0 is plugging 0 in this polynomial, then we get function value is 1. Therefore, condition 1 in the checklist is satisfied. Now, I turn to have a check with the second condition, whether or not the both side limit S0 exists. Because the function is defined on the left by this polynomial, on the right by this polynomial. So on the both sides of the point 0, the function is defined differently. Instead of computing the both side limit as 0, I compute left-hand side limit and right-hand side limit as 0. When x approaches 0 from the left, that means that x is less than 0. When x is less than 0, this is the function. So we have this equation. Now to find this limit, plug in 0 in x, then the limit is this number. This number is 1. Now right-hand side limit is 0. X approaches 0 from the right side. From the right side, that means that x is greater than 0. When x greater than 0, the function is this. So plug in 2x to the third in x, in the function f here. Then we have this equation. Now to find this limit, plug in 0 in x, then the limit is this number. This number is 0. So when x approaches 0 from the left side, the function approaches 1. When x approaches 0 from the right side, the function approaches 0. Two different limits. Therefore, the both side limit at the point 0 doesn't exist. Limit should be 1 and only 1. When x approaches 0 from the left, we have one limit. When x approaches 0 from the right, we have a different limit. So both side limit doesn't exist. Therefore, condition 2 is not satisfied. Therefore, the function is not continuous at the point 0. Actually, at the point 0, the graph of the function has a jump. Based on the information in part A, we can roughly sketch the graph of this function. At x is 0, function value is 1. So there is a solid point here. When x approaches 0 from the left side, function approaches 1. So on the left side of the point 0, the graph approaches this point. The height of this point is 1. When x approaches 0 from the right, function approaches 0. On the right of the point 0, the graph approaches this point. The height of this point is 1. From this diagram, we can see that the function f is continuous at the point 0 from the left side because solid point is here. If the solid point is here, then the function is continuous from the right side. But now solid point is here, so continuous from the left side. Now, part C. Over what intervals the function is continuous? From this diagram, the function is continuous from negative infinity to 0. At 0, the graph is continuous from the left side. So I put a square bracket here. Square bracket means including 0. Then the second interval is 0 to infinity, 0 to infinity. At 0, the function is not continuous from the right, so I place a parenthesis here. Parenthesis means excluding the point 0.